Hello everyone, welcome back to another SLHL IB Chemistry video 2025 specification. Today we're going to be looking at structure 1.4 upon special request. I trust you can read. If you want to read that, pause the video. Otherwise, let's get straight into it. So 1.4.1, what you have to know is what is a mole? So a mole is a unit expressing an amount of substance, and 1 mole is equal to the number of elementary entities. This can either be your atoms, molecules, ions, electrons, etc. in comparison to 12 grams of pure carbon 12. This number, the mole, Avogadro's constant, which is exactly 6.022 times 10 to the power of 23, which is a pretty big number. So this constant, also referred to as an A, will be given to you in your booklet. So to find the number of elementary entities, the formula that you will need to know is entities equals moles times Avogadro's constant. So let's just use an example of how many atoms are in 2 moles of oxygen. So number of entities equals moles times Na. So we have 2 moles, and Avogadro's constant will be 6.022 times, which gives us 1.204 times 10 to the 24. Secondly, looking at 1.4.2, we have to know the definition of AR. So this is the atomic mass, and 1 unit of atomic mass is defined as 1/12 of the mass of carbon 12. Something we need to keep in mind is that isotopes of elements will have different atomic masses as a result of their different number of neutrons. So in terms of calculating AR or AR abundance of different isotopes, let's say we have chlorine 35 with a mass of 34.97, and chlorine 36.97 as well. Percentage abundance 75, and then 24.22. So how would we calculate the AR of these 2 isotopes? So we will take our mass and multiply it by our percentage. So 34.97 times our percentage divided by. So we will take our mass and our percentage. We convert our percentage back to a decimal and multiply these 2, which will give us 26.5. And we'll do the same for our chlorine 37 isotope here, which will give us 8.96. So then we'll have to sum the products to get the atomic mass of chlorine. So 26.5 plus 8.9 will give us 35 0.46. Now, another way in which we can do this is simply by turning this into one big equation where we take our percentage abundance. So 34.97 times 75.78 plus our other mass and percentage over 100, which will also give you the same answer. Now, MR, similar concept to AR, except that it applies to compounds. And in terms of the calculations, it's quite similar. So if you were to find the MR of, say, H2O, what we'll have to do is essentially add up the ARs of each element within this compound. So 1.01, that's hydrogen, times 2, plus 16 of oxygen, which will give us 18.02. For 1.4.3, we have to know how to calculate molar mass from mass and MR. So, molar mass, or just moles. So to calculate this, you will do moles equals mass over MR. So let's just do a quick calculation using this. So let's say that we have 2 grams of our water, so 2 grams, and our water was 18.02. Let me do that calculation real quick. Can't do that in my mind. 2 divided by 18.02. Not very nice number. 0, let's just round that up to about 0.11 moles. Secondly, we need to know what SI units are. So an SI unit, or SI, is the accepted unit system for consistent measurements of physical quantities. So this is like your kg for mass, your A for amperes, A for current, and within your SI, you can have derived units, which is the combining of these base units, such as meters squared, which is just meters times meters for area. And you will also have your prefixes to represent fractions of units, such as C for centi, which maybe you've seen in CM, or M for milli, which you've probably seen in MM. In 1.4, what you will need to know is to calculate empirical and molecular formulas. So let's just differentiate the two before we get into this. So an empirical formula is the simplest whole number ratio of atoms in a compound, which is not necessarily the molecular formula. So it's the simplest ratio of elements in a compound. So let's just take the example of, okay, we all got 30.4% of nitrogen and 69.6% of oxygen. So we will take our percentages and use them as our mass. In this over here, our moles equals mass over MR. So if moles equals mass over MR, we will do 30.4 divided by the MR of nitrogen, which is 14.01, giving us 2.17. And for oxygen, we will do the same thing, 69.6. 69.6 over, 16, which will give us 4.35. We'll divide our biggest number here by our smallest numbers to give us our mole ratio. So 4.35 over 2.17 gives us about 2, telling us that we have a 1:2 ratio between nitrogen and oxygen. So the empirical formula of this would be NO2. Another nice way in which you can do this in a more organized fashion would be by drawing yourself a little table where you got mass, MR, mole, and ratio. The mass Mr. Mole's ratio table, as some people like to call it, because that way you will know you have to divide your mass by your MR to give you your moles, which will then give you your ratio. It's just a nice way to organize it if you so choose. So to calculate the molecular formula of say this empirical formula right over here, when we know that the whole thing should have an AR of 90 grams per mole, so an MR, correction, that's molecular formula. So 2 carbons, that I'm just going to do 12.01 times 2, giving us 24.02. Hydrogen, 1.01 times 5, 5.05. And then oxygen, 16 times 1, just 16. Sum the 3 together, and that's going to give you 45.07. Now, we'll divide our supposed MR by our MR shown in the empirical formula, which will give us about 2, telling us that we will need to multiply all of these numbers by 2, meaning that the molecular formula of this compound will be C4H10O2. On to topic 1.4.5. So, molarity, often represented by the capital M, is the number of moles of a solute per decimeter cubed or liter, that's or liter, of a solution. So if you are wanting to find, for example, the grams per decimeter of a solution, you should measure your volume in centimeters cubed and then divide that by 10 to the power of 3 to convert to decimeters, and then proceed in your calculations. So let's just get an example of what calculating molarity would look like. Say we have 10 grams of salt, NaCl, and it is in 0.5 dm3 of H2O, so it's an aqueous solution. So we know that our mass of NaCl is equal to 10 grams. So let's convert this to cubic decimeters, and we know that our cubic decimeters are 0.5 dm3. So if we take our 10 and divide it by 0.5, we get 20 grams dm3. 3, telling us that the concentration of the NaCl in this aqueous solution is of 20 grams per decimeter cubed. Also, just so you know, the formula N equals CV will be one that is given to you in your exams. And one final point that we have to know before wrapping up this little subtopic is that in chemistry, when you use square brackets, such as these, maybe you've seen them before in maths, these are used to indicate concentration. So if you were to write the concentration of, say, HCl, and you had 1 molar of it, you would do HCl in your square brackets equals 1 m, which tells us exactly that there's 1 molar of HCl. On to our next and final point under this area of the specification, I believe, yes, we have to know about Avogadro's law. So Avogadro's law states that equal volumes of all gases under the same conditions of temperature and pressure all contain the equal number of molecules, which means that two gases at the same temperature, even if they are of different elements, will contain the same number of moles. Avogadro's constant, as I stated earlier, is 6.022 times 10 to the power of 23, and this will be a constant that is given to you in the exam. Avogadro's law can be applied in this example in which we have 2 balloons. So balloon A has half the volume of balloon 2A, and balloon A has oxygen, whilst 2A has hydrogen, which means that we have a 1:2 ratio in terms of moles. Now this is helpful because this means that we can easily calculate the amount of moles in one balloon, given that we have the number of moles in the other. So if we are told that we have 0.5 moles in our oxygen balloon, we can simply times this by 2 to give us the moles in our hydrogen balloon, which will be 1. Thank you for watching, and I hope that could help.